Welcome to The Explainer. Today, we're diving into an idea that's so fundamental, you probably don't even notice it's there. It's kind of like the hidden operating system for reality itself, organizing everything from your Spotify playlists to, well, the entire digital world.
So, let's start with a problem we all have, right? Our world, it's just overflowing with stuff. Data, objects, ideas, it's a total mess. How do you even begin to make sense of it all?
Well, the answer is actually something we do without even thinking about it. To cut through all that chaos, we put things into groups. We make little collections to manage and understand everything around us.
And this basic instinct actually has a fancy name, set theory. But don't let the name scare you. It's really just the official language for what we already do, thinking about things in groups, or let's call them collections.
Okay, so for a collection to be a proper set, it has to play by two really strict rules. First, everything in it, the elements, has to be well defined. And second, they have to be distinct. That means no duplicates allowed. Your music playlist is the perfect way to think about this, right? You know exactly which songs belong, and you'd be pretty annoyed if the same track played twice in a row.
And this, right here, is the key. Absolute clarity. For something to be a set, the rule for what's in or out has to be rock solid. The planets in our solar system? Yep, that's a set. You're either a planet in our solar system or you're not. No debate. But beautiful girls in Africa? See, that's not a set. Why? Because beautiful is totally subjective. What I think is beautiful, you might not. Same thing with songs by Queen, that's a perfect set, versus the totally vague, good songs. Whose definition of good are we even using?
And that second rule about no repeats, it's just as crucial. Every single element has to be unique. That's why this example here, set B, isn't a real set. See that extra 3? It's a duplicate. It's literally the same logic a database uses to keep its information clean and reliable. No duplicates allowed.
Okay, so we've got a handle on what a set is. Now let's get into the grammar of sets, the different ways we can actually describe these collections and start to see how they can relate to each other.
So you've got 3 main tools in your kit for describing a set. You can just say it out loud, in plain English. That's the verbal method. For smaller sets, you can just list everything out. That's called the roster method. But for the really big or more abstract collections, you use a rule, a property that every single member has to follow, and that one's called set builder notation.
Now, this idea is super important. A subset is basically a smaller set that's completely contained inside a bigger one. Think about it. If every single song on your 80s rock playlist is also in your giant entire rock music collection, then yeah, your 80s list is a subset. Simple as that.
Okay, this is where it gets really powerful. Set theory isn't just about tidying up. It's about creating new things. We can perform these things called operations on our sets. We can combine them, compare them, and pull out brand new insights from the collections we already have.
First up, we have the union. And check out the symbol. It looks like a U for union, so that's super easy to remember. Just think of it like merging 2 playlists. You're just mashing them together to make one big super playlist that has all the unique songs from both. All right, let's look at an example. Here are our 2 starting sets. On one hand, we have set A, which is all the numbers that divide evenly into 12. And then we have set B, which is all the odd numbers less than 12. So what happens when we combine them?
And there it is, the union. We've got every single element from both sets all in one place. But look closely. The numbers 1 and 3, which were in both sets, they only show up once here. That no duplicates rule, it's always in effect.
All right, next up is the intersection. Now this one is all about finding the overlap. It only cares about the elements that 2 sets have in common. It's perfect for answering a question like, hey, which songs are on my workout playlist and also on my party playlist?
So if we look at our 2 number sets again, the intersection is pretty straightforward. The only numbers they both share are 1 and 3. That's it. That's the whole intersection.
And our last basic operation is difference. This is how you find out what's unique to the first set you mentioned. You're basically taking set A and just removing anything that also happens to be in set B.
So for A minus B, we start with everything in A. That's 1, 2, 3, 4, 6, and 12. Then we look at B and take away the shared numbers, which were 1 and 3. And what are we left with? Just the elements that are exclusively in set A.
All right, let's step it up a notch and look at a couple of what you might call power user concepts. These are the tools that let you explore every single hidden possibility within your collections.
Okay, the power set. This idea is kind of mind-bending, actually. It's the set of all possible subsets of your original set.
Think about that. It's a collection of every single combination you can possibly make, from an empty set to sets with just one song, all the way up to the entire original playlist itself. It's the ultimate catalog of what's possible.
Now for something called the Cartesian product. Let's switch to a new analogy to make this super clear. Outfits. Imagine set A is all your shirts, and set B is all your pants. The Cartesian product gives you every single outfit you can possibly make. You just take the first shirt, pair it with every single pair of pants. Then you grab the next shirt and do it all over again.
And this is what it looks like in practice. We take our first element from set A, which is the number 3, and we systematically pair it with everything in B, 0, 1, and 2. Then we take the next element, 4, and do the exact same thing. What you end up with is the complete set of every possible ordered pair you can make between them.
So, okay, we've talked about playlists, outfits, little number games. You might be thinking, why does any of this matter in the real world? Well, the answer is huge. This simple, fundamental logic is the invisible engine running our entire modern world.
So here's the bottom line, the big idea. You use sets to organize information with clear rules. You use operations like union and intersection to manipulate that information and ask questions. And then you build on that. This exact framework. Organize, manipulate, build. It's not just some abstract math idea. It is the absolute core logic behind every database, every Google search, and pretty much every piece of software that has to manage information.
So I'm going to leave you with this thought. Now that you know the language of sets, start looking for them. I mean, everywhere. In your work, your hobbies, your day-to-day life. Start defining your world into collections. Because honestly, knowing how to organize and question those collections, it's not just a neat trick. It's a genuine superpower.